What lessons can we deduce from chance and commonplace settings? To begin, we start with a discrete sample space. This is a space which is either finite or denumerably infinite. We could, via our dictionary of translation, identify the sample points of such an experiment either with natural numbers or with integers. It'll transpire that in many settings, the particular name we give a sample point is of little matter. What matters are its chance connotations, and therefore, in many settings, it'll be preferable to make the problem antiseptic and simply identify conceptual outcomes sample points with integers. So we start with a discrete sample space. Given a discrete sample space, the first item of business in constructing a probability measure is to identify atomic probabilities. We start with elementary events called atoms, which consist of singleton events, events consisting of a single sample point. And to each such sample point, say omega k, to the corresponding atom, we allocate a probability, an atomic probability. Of course, this will only depend upon the particular sample point under consideration, say the kth sample point. And therefore, let us call the atomic probability attached to the sample point omega k, p of k, where we use a lowercase p to denote an ordinary function of an integer argument. Now, what do we need from these atomic probabilities? Well, manifestly, they are probabilities, and therefore they have to satisfy positivity. And furthermore, these probabilities have to satisfy normalization. They have to add to 1. So, we start with atomic probabilities, which are positive, and add to 1. Now, how do we go about constructing event probabilities in general? Well, we start with any event, and we can think of an event in a discrete space as being the union of a discrete set of atoms. And so, manifestly, if a probability is to be assigned at all, it must be given by a sum of probabilities. How do we go about doing this? Well, the notation on screen says sum over all the sample points inside that event the probability of the corresponding atoms. If the event A under consideration consists of, let us say generically, the k1th sample point, the k2th sample point, the k3th sample point, and so on, for example, the second sample point, the 5th sample point, the 19th sample point, then one would simply add the probabilities of the atoms corresponding to the 2nd, the 5th, the 19th, and so forth. This, of course, we realize is our third fundamental axiom, the axiom of additivity. Let us now summarize what this means for our purposes. So, to characterize chance in a discrete setting, we begin first by identifying atoms, singleton events in the space. And our fundamental realization is that in discrete spaces, atoms are the carriers of mass. Notice we are very freely borrowing from the language of physics. Now, how do we go about allocating mass? Well, to each atom, let's say the kth atom, we allocate a probability p of k. The atomic probabilities determine a function p of an integer. We call this, again borrowing from the language of physics, a mass function or a distribution. This function must satisfy the key axioms of positivity and normalization. Given such a mass function, how do we go about constructing probabilities? Well, very simply, the probability measure allocates to any particular subset, any particular event in the sample space, a probability obtained by summing the atomic probabilities corresponding to that event. The whole is manifestly the sum of its distinguished parts. Very simple, very clean. At this point, it becomes clear that in a discrete space, the experiment can be captured in a very, very, very simple way. Right? Now, this is a political age, and therefore we need some slogans to go along with our course. So here's our slogan. Any honest mass function p of k, defined on the integers, induces a discrete probability measure for some space. What is an honest mass function or honest distribution? Well, what makes it honest is that it satisfies the fundamental axioms of positivity and normalization. With such a mass function in hand, all we do to construct probabilities is simply add up atomic probabilities for the event at hand.